What if scientists just proved that time travel is possible without paradoxes? In 2025, physicists published a breakthrough model that could allow time travel to exist within the laws of physics. No broken logic, no grandfather paradox, no erased timelines, just a consistent, mathematically sound way to move through time. For over a century, science has inched toward this possibility. Now, with new discoveries combining Einstein's relativity, quantum mechanics, and thermodynamics, that dream might finally be within reach. But to understand how we arrived here, we need to start from the beginning. From a young physicist in 1905 who first discovered that time doesn't flow the same for everyone. In 1905, Albert Einstein published his theory of special relativity, changing how humanity understood time forever. Before him, people believed time was absolute, that it ticked the same for everyone everywhere. Einstein proved that wasn't true. He showed that time slows down the faster you move, a phenomenon now known as time dilation. This isn't theory anymore. It's been proven. Astronauts on the International Space Station actually age a little slower than people on Earth because they're traveling so fast in orbit. When they return, they've technically time traveled into the future by a few milliseconds. Einstein illustrated this with a thought experiment called the twin paradox. Imagine two twins. One stays on Earth while the other travels into space near the speed of light. When the traveler returns, they find their twin much older. The reason is simple. Time passed slower for the traveling twin. That may sound like science fiction, but experiments with atomic clocks confirm it. In 1971, scientists flew synchronized atomic clocks around the world on airplanes. When compared with clocks left on the ground, the flying clocks had ticked slower, exactly as Einstein predicted. We see this effect every day in technology. GPS satellites orbiting Earth must correct for time dilation to give accurate location data. Without those corrections, navigation systems would drift kilometers off course daily. Einstein later expanded his theory into general relativity, showing that gravity also slows time. The stronger the gravitational field, the slower time moves. Near a black hole, time almost stops relative to the outside universe. This means that the cosmos naturally allows tiny forms of time travel, just not yet the kind we see in movies. Einstein's discoveries shattered the idea that time was fixed. Instead, time became flexible, stretching and bending under motion and gravity. Every person carries their own time, flowing at its own rate. This was the seed of time travel science. Einstein himself doubted time travel to the past could ever be practical, yet his equations didn't forbid it. They described paths through space-time called closed time-like curves, which could, under extreme conditions, loop back to an earlier point. The math allowed it, and later scientists would spend decades trying to figure out how to make it real. In 2025, a team of physicists led by Andrei Zelnikov published a paper in Physical Review D that reignited interest in time travel science. They proposed a new kind of spacetime structure called a ring wormhole, a stable tunnel through spacetime that might allow travel between 2 points in time without violating physics. A wormhole is like a shortcut through the universe. Imagine folding a sheet of paper so 2 points touch and drawing a hole through them. That hole connects distant places instantly. Wormholes were first theorized by Einstein and Nathan Rosen in 1935, but those early models collapsed too quickly to use. Zelnikov's breakthrough was finding a stable version that didn't require impossible materials. Older models needed exotic matter with negative energy to keep them open. His model, however, used natural quantum effects, tiny fluctuations in the vacuum of space, to stabilize the wormhole. Here's the fascinating part. If one end of the wormhole experiences time differently than the other, say by moving near light speed or sitting in a strong gravitational field, time could pass slower at one end. Traveling through the wormhole would then let you exit at an earlier or later point in time. In other words, the ring wormhole could act like a time bridge. This model also avoided the classic grandfather paradox. the idea that going back in time could erase your own existence. Zelnikov's equations built in a form of self-consistency. You could travel back, but events would always adjust themselves to keep reality coherent. You couldn't change history, only participate in it. The scientific community reacted with excitement and caution. The discovery didn't mean we can build wormholes tomorrow, but it showed they might be physically possible. That alone was groundbreaking. Zelnikov's work also connected with earlier theories by Kip Thorne and Stephen Hawking. Hawking once argued that the universe might have a chronology protection mechanism to prevent paradoxes. Zelnikov's model supported that, by showing that if time travel exists, it likely obeys the universe's own self-correcting laws. This was the first credible, paradox-free mathematical model of time travel that didn't break known physics. But it was only the beginning. To truly remove paradoxes, scientists had to combine relativity with another field, quantum mechanics. Einstein's relativity explains the large-scale universe, stars, gravity, spacetime, but the tiny world of atoms and particles follows quantum mechanics, where reality behaves unpredictably. The challenge has always been merging these two worlds. In 2025, physicist Lorenzo Gavesino proposed a model that finally connected them. His idea, called quantum-informed time travel, merged general relativity, quantum mechanics, and thermodynamics, the science of energy and entropy, into one framework. According to Gavesino, paradoxes disappear when you view time travel through quantum rules. In quantum mechanics, particles don't have definite outcomes until they're observed. They exist in a cloud of probabilities. This means events aren't locked in one timeline, but can coexist as possibilities. So if someone traveled to the past, the universe wouldn't break. Instead, quantum probabilities would reshape themselves so that cause and effect stay consistent. The traveler's actions were always part of history, just like Zelnikov's self-consistency principle, but now supported by quantum law. This elegantly solves the grandfather paradox. You can't erase your own existence because quantum mechanics ensures that all events fit within one coherent history. Reality adjusts to maintain logical order. Gavesino's work also explained time as a thermodynamic process. The arrow of time, why we move from past to future, is tied to entropy, the natural tendency toward disorder. Traveling backward wouldn't destroy this arrow, it would simply shift perspective within the same system. Channels like Kurzgesagt in a nutshell popularized this idea, explaining that the universe may not forbid time travel, it just organizes it in ways that keep physics consistent. Quantum-informed time travel doesn't rely on fantasy or breaking the speed of light. It suggests time itself might be flexible within quantum boundaries, and that paradoxes are illusions caused by our limited understanding of causality. For the first time, scientists had a picture of time travel that combined Einstein's geometry with quantum logic, and the mathematics behind it pointed towards something even astonishing: that time travel might already be encoded in the structure of spacetime itself. In recent years, physicists Germain Tobar and Fabio Costa from the University of Queensland provided one of the most exciting mathematical proofs for paradox-free time travel. Their 2020 study on closed time-like curves, paths through spacetime that loop back to their starting point, showed that time travel can exist without contradictions. Their equations demonstrated that events naturally self-correct. If you tried to change the past, your actions would become the cause of the events you were trying to alter. For example, if you went back to stop an accident, you might become the reason it happened. Cause and effect always align. This concept is similar to how feedback loops work in nature. Systems tend toward balance. Tobar's math showed that time is no different. It preserves logical consistency no matter how it bends. Adding to this, in 2022, Google's quantum computing team simulated a simplified wormhole on a quantum processor. It wasn't a real wormhole, but the quantum system behaved as if information had passed through a tunnel in spacetime. It was a tiny, artificial glimpse into how the universe might manage time and space at once. Together, these discoveries painted a striking picture. Time travel could exist mathematically, physically, and logically, without paradoxes. The challenge now isn't proving it's possible, it's finding a way to harness it. If we ever learn to manipulate quantum spacetime safely, we might send messages, particles, or even ourselves through time, not in fantasy, but in science. If time travel is possible, why haven't we seen anyone from the future? It's the most common and natural question, one that even physicists ask. One explanation comes from research by Andrew Jackson and others who study timeline instability. Their models suggest that time travel might be so sensitive that even the smallest disturbance destroys its stability. Only self-consistent timelines can exist. Others collapse instantly. Another idea comes from Stephen Hawking, who once held a time traveler's party, sending invitations only after the event. No one showed up. His point was simple. If time travel to the past were easy, we'd already know.
But modern physics gives subtler answers. It could be that time travel only works at the quantum or microscopic level, too small for humans to experience. Or that wormholes, if they exist, can only connect points forward from their creation, not before. In that case, no traveler could ever arrive in our present until the first time machine is built. There's also the possibility that we're missing the signs entirely. If time travelers are bound by self-consistency, they wouldn't appear as anomalies. Their actions would already be part of history, hidden in plain sight. In the end, the absence of evidence isn't evidence of absence. Time travel, as 2025's discoveries suggest, may not violate physics. It simply requires conditions far beyond our reach. Einstein gave us the foundation. Zelnikov, Gavasino, and Tobar built the next layers. Together, their work suggests something profound. Time is not a straight line. It's a dynamic, flexible dimension that might allow motion in ways we're only beginning to understand. Maybe one day, centuries from now, someone will watch this documentary from a future where time travel is as common as air travel. And perhaps they'll smile, knowing that it all began here, with a few curious humans asking the most impossible question. What if time travel is real and always has been?